Last time we had just barely dug into the surface. This is one of the figures that we looked at last time that represents the way a synchronous generator works. We have major pieces, stator, rotor. The piece on the outside doesn't turn, the piece on the inside does. We have the stator windings, which are embedded in the static part of the generator, and those are the ones on which we have the currents flowing that are actually going out to the equipment in the field. The field winding is within the rotor. There's going to be 3 phases of stator windings. There's only going to be one set of field windings. The field windings are going to be need to be excited. Okay, essentially, there needs to be a DC current flowing through them, or else we're not going to be generating any magnetic field. And usually, what happens is beyond startup, some power that's being generated by the unit will be siphoned off, run through a rectifier, and used to excite the field winding. So we run current through the field windings, which causes this magnetic field, our excited magnetic field. And because we rotate the rotor, the flux linkage between the field winding and the stator winding is going to change, right? Our goal is to excite a voltage or generate a voltage differential at the output of the stator terminals. So if the generator didn't turn, the flux linkage would be constant, which means there wouldn't be any voltage generated. So it's the rotational motion that actually causes the D flux linkage dt. And then here you can also see physically what's going on with respect to the directions of the currents and the directions of the magnetic fields. Right? We can use right-hand rule to show that the red arrows are the magnetic field that would be generated by the current in red. The excited or induced stator current has a direction that is opposite to that, again following right-hand rule, and what we see is in the end these two magnetic fields sum to 0. Okay, and so that is really a good explanation of the way that a synchronous generator works. This other picture just gives a little bit more of an in-depth view of the placement of the different stator windings, the different axes, which will come into play. We will talk about the direct and the quadrature axes, the D and the Q axes, and so on. Last thing, I feel like I should, even though we're not going to have a chance to talk about it, I did mention it last time, the difference between a round rotor and a salient pole rotor. And so the salient pole essentially has this notched out area around which the field windings are wrapped. And we're not, for better or for worse, going to have too much time to talk about that in this class, but it is something to be aware of. We'll be mostly focusing on round rotor designs. Okay, so I'm actually just going to continue this same set of notes since we only got like a little bit into it. As opposed to embedding those figures in the notes, it hasn't come out well when I've tried to do that. I'll just leave them in the Dropbox with the rest of the notes so you can pull those figures up. Okay, so now getting into the bigger picture. So figure 9.1 from the textbook shows a steam-powered generator, which was the norm, still is the norm for a large part, but really was the absolute norm for a better part of, the last 100-something years. This idea that we take fuel, we heat it up, we generate steam, run the steam through a turbine, and that provides rotational energy to generate electricity. So we start off with heat. Okay, heat coming in to some sort of a boiler. And this is going to be a system level diagram. We're not going to spend too much time, if any, really on the thermodynamics of this. Not because it's not important, but it's just sort of topic. It's a topic for a different class altogether. So we have the heat coming into the boiler, out of the boiler, and this is a closed loop. So I'm starting at this point, and then we'll work our way back. So out of the boiler, we have steam at high pressure, right, and speed. Well, I guess they imply one another. And that goes into our turbine. And I don't really have any information prepared to talk about the structure and operation of a turbine. Is everybody pretty familiar with, you know what a turbine is, right? It's essentially, yes, no? Yes, okay, right. It's essentially just, right, has a cone shape and sort of, it's like the things they use to, it sort of looks like the things they use to mix like ice cream or whatever, right? It sort of funnels the steam up and causes rotational energy, or causes the unit to rotate. Okay, so we got the high pressure steam going into the turbine. Then we got that steam coming out. It's going to be at a lower temperature. It will lose a lot of its energy going into a condenser. I think it's OR, condenser. Coming out of the condenser, we will have some heat being generated or recuperated from the steam. We'll talk in a second about whether there's any way we can use that. Then we will have our pump. And this is going to be our low temperature steam / water. And the pump is going to push the water back up into the boiler. Okay, and so this continues in continuous operation. Heat in, heat out. And so what can we potentially do with the heat out? Does anybody know what we could potentially do with that? Yeah. Reuse it, okay. Now there's some reasons why they don't just leave the heat in the steam and run it through like that. So let's go through, let's use the assumption that we're going to be using the condenser to extract the heat from this internal loop. So when we say reuse it, we could reuse it as heat or...
I went to the technical seminar with the power plant, although I couldn't really hear much, but they were inside of the, in the generator, but this, all this steam is rerouted to use to generate hot water for the campus.
Yeah, that's one option, most definitely. Have you ever heard of the term a cogeneration plant? So cogeneration is essentially this idea that we take this heat and we run it to another smaller generating unit and repeat the same process. A generating unit that doesn't potentially need that. So this main unit that we have requires steam and steam at very high pressure and very high heat. Then we take the heat, which is not going to be as high, right? Whatever it was X degrees before, now it's X divided by 2. And we'll route that to another smaller unit that can run at a lower temperature, but still generate some electricity. So that's one option, is to take this heat and run it to a cogenerating unit. Now, if you are somewhere like a college campus or a hotel or something like that where you do have a need for hot water directly, then yeah, I mean, that would definitely make sense. And then, so we forgot about the other part of this process. So we have our shaft. Now this is going to be running to our synchronous generator. Just like the machine that we've been talking about the last half a class or so. And that's going to generate our phase A, phase B, phase C voltages. So that's an idea of how power is generated in a traditional steam unit. I say 20 kV approximately being generated. That's for large units, not counting distributed generation or renewable based. That would be the level within some percentage of the level at which it would be generated. The idea is that the electricity being generated by this unit is most likely going to be immediately transmitted over a long distance. Okay. More times than not, if this were nuclear or coal or something along those lines, it's not going to be anywhere really close to the loads that need it. So it's generated at a high voltage. It'll most likely, when it enters the transmission system, be bumped up to an even higher voltage and then transmitted over 50, 100, whatever miles is required before it reaches the load center. Okay, so I'll let this thing move up any further. It's weird. I don't get it. What is this? right, I'll just start a new page.
Maybe it's like insert more space. and
How?
insert tab.
How do you do it?
Under the insert tab, the top.
Under Insert tab.
Just right one.
Is that what it is? Usually I'm able to. Okay, all right, that makes sense. I've been using this for quite a while, like doing the notes. I've never seen it do that. Okay, all right. So next thing here, structure. I don't want to rewrite a lot of the stuff that we've already talked about. So the stator, armature windings, three-phase. We have the rotor and the field winding, and we have the air gap. I'm not going to rewrite that stuff. We showed that in the picture. We're going to focus on two-pole machines. We talked about that last time, the difference between a two-pole and a multi-pole machine. Right? Two-pole would be like the example we had where it was just 3 sets of armature windings. If it was a multi-pole machine, then we would have 6, 9, whatever, some multiple of that, which then would allow the rotor to turn at a slower speed and generate electricity at the higher frequency at close to 60 hertz. And then, right, it makes sense to create the generator itself from a material that has a high permeability and a very small air gap. Right, we want to maximize the amount of energy that is that flows from the field winding across the stator windings, and we want that mutual inductance to be much, much higher than leakage. Okay, so stator with 3 windings. The way that, so we're going to be representing our stator with the windings collapsed into a single point. Okay, but in reality, this is not the way that it looks. So if we were to talk about, let's say this is a phase A winding. So we're going to represent the stator windings by a single point, which will be like the green here, in the middle. But in reality, the stator windings, well, first off, you can't ever, you couldn't have multiple unless there was just one winding, right? One turn, you wouldn't be able to collapse it all into one spot. But the actual way that the windings are distributed is sort of this sinusoidal nature. So very, very close together on the two ends, and then very, very far apart in the middle. And the reason why you can say sinusoidally is it's sort of like, right, 1 down to 0, up to 1 if you're looking at the concentration or how close together those windings are. So the phase A winding actually does encompass the entire stator. Okay, so figure 9.4 provides us a simplified view of the generator. Now, there are lots, if you remember if any of you have me for electronics, or I guess all the electronics classes should be teaching this, but how there's different models, right, that can be used to represent a component or a device, and they can have, one's not right, one's not wrong, they're just used for different applications. So for the generator, you can have very, very complex models. In graduate school, in one of the more advanced modeling classes, there's a 27th order generator model. So there's 27 variables just to represent the way that the generator operates. Obviously, we're not going to be doing that. And our goal is going to be to try to find a low complexity but reliable and accurate model for the generator. And that's going to involve us using a transformation, a mathematical transformation between a static point of view and a rotating point of view. So it helps in the modeling of the generator if we, again, if we change our point of view to assuming that the rotation is occurring. So a simplified view of the generator looks like this. We have our rotor assumed to be rotating at a constant speed, okay, omega synchronous, and we have what we can think of as just 3 inductive coils embedded in the stator. We have IA, IB, and IC. We'll have names for this. We'll call this the A axis. Call this the C axis. And then I don't really have room, but you can see that would be called the B axis as well. And as you can assume, right, there's going to be 120 degree separation between those. So, and then one thing which is not drawn on here, but I probably should put, is our field winding. So we're going to be looking at this as really just a set of inductors rotate. Okay, so next piece. Rotor with field winding. So we've talked about the stator. So the rotor, again, contains the field winding with the excited current which we're going to call IF. This is a DC current. And excitation is going to play a major role in controlling the generator unit. Does anybody remember from last time where or what aspect of the generator's operation the excitation has the greatest effect on? So we saw that there was two main relationships. Okay. To control the amount of real power that's being generated, that's more closely related to what? The energy or the rotational torque coming into the rotor itself, right? Which makes sense. If you want to generate more real power, usable power, you need to increase the amount of heat going to the boiler, increase the pressure and speed of the steam, increase the amount of rotational energy in the turbine, and that will give you more real power. Reactive power, on the other hand, okay, which is closely correlated to the voltage magnitude at the terminals. So both of those, they go hand in hand. That's going to be primarily controlled by the excitation system. So you're going to be increasing, decreasing the amount of DC current that's applied to the field windings in order to play around with that value. So what we see is that the P generation is closely related or is dependent on mechanical power. And the Q generated is dependent on the excitation. Okay. So the induced EMF on the stator windings, this is really what we're concerned with. We don't care too much about the internal operation of the generator as long as we have a good understanding of how much power is being sent out to the system and what is the voltage and the current that's associated with that. So we're going to start off by looking at a single phase example. So we'll draw a generator, we'll draw the relevant magnetic fields, we'll talk about the mutual inductances and how our EMF is generated, and then we'll branch out and move on to the other two phases. Okay. I know I keep drawing pictures that are very similar, but each one has a little bit of a different focus in terms of what pieces and what information is shown. Okay, again, right, we have our this is going to be our phase A current that's going out, phase A current that's going into the stator. We have our A axis. If you remember, we drew that on one of the other and we have our electric field, our magnetic field, which looks like this. And this is the magnetic field that's generated by the the stator, the field winding. And so if I were to draw the field windings, again, it uses that sinusoidal distribution, but really what we're concerned with is the we'll, again, like we're doing for the stator winding, be focusing on, we'll collapse all of these points down to here and here. So it uses that sinusoidal distribution, but equivalently, we can model it as these two single points. And that's the reason why you see the electric field, the magnetic field, being generated as such, right? Because the magnetic field would go through the center of the coil. So if you imagine that the coil is doing that, then the magnetic field would be flowing that way. And if we want to follow the right-hand rule, that means that, well, I can't really draw that in this picture because I didn't give it the right angle. But and then we have our EA of T plus minus. Okay. One thing that we haven't shown before is we also have another axis to be concerned with. That's the F axis, the axis of the field winding, which is going to be the same as what we called previously the D axis. So the F axis is the same as the D axis. F Q. Thank you. F representing the axis corresponding to the field winding. D axis meaning the direct axis of the rotor. It's same thing. Okay. So if we try, so let's try to draw the resulting IA waveform for this picture above. Okay, now what I'm going to do is I'm going to outline, okay, let's see, 1, 2, 3, 4, 1, 2, 3, 4. So this point here is going to represent when the F and A axes align. So if you think about it like this, here, the position that they're at, right, the F and the A axes are perpendicular to one another, right? Which means what, with respect to the mutual inductance between the field and the A-phase windings. So how much of the magnetic energy generated by the field winding is going to be quote-unquote caught by the A-phase winding when it looks like this? So if you think about it, right, this coil looks like this. The other one looks like that, if you can imagine my hand being like a cylinder. This is the worst case scenario, okay, in terms of trying to the mutual inductance will be at the minimal value, right? There'll be very little magnetic energy that will be flowing out from the field winding to the A phase. The maximum is when they are aligned, right? We saw that example going way back to all the stuff that we did in Chapter 2 related to the magnetics, right? It's almost like a pipe. The water goes through the center, and if you want to catch that water or catch that magnetic field, it needs to be lined up. So, when this thing rotates by 90 degrees, the coils will line up, and the F axis and the A axis will be aligned with one another. Okay, so that's the point that's right here. So this is when F axis and A axis are aligned with one another, and then I can draw another line which will be when they are perpendicular. I definitely misspelled the word perpendicular, but is it P-I-N? Perpendicular? Is that right? I need autocorrect when I write by hand. Okay, so let's ask ourselves a question. We're drawing IA. Let's just go with maxes and mins, okay? Where do we expect the max of IA to be? Yeah. When they line up, right? Where do we expect the min to be? Where they don't line up. Okay. So, and then over here, we'll have another instance of them lining up because, right, the coils are not, they're not directional, right? They can line up like this or they can line up like that. However, it will have an effect on the polarity, right? Because it'll be flipping the direction of the terminals with respect to the field winding, right? If we have it like this in the beginning, it's IA is positive with respect to IF, and if you go over here, IA is negative. So we'll have another point where the mutual inductance is maximum, but flipped, and then 0. And anyway, you can see here, right, we can draw our IA value. So this is one way of sort of understanding on a conceptual level what's happening when we generate this energy. Okay, so next question is how do we define the induced EMF? So the induced EMF see if I can turn the brightness. It'll help me save some energy. So the induced EMF polarity is chosen to be positive right, we have passive sign convention, which is for passive elements, right? It says that, if I draw it over here real quick, right, if you have a resistor and you have your V plus minus, your current runs in that direction. And then for active elements, things that are injecting energy into the system, we often use the opposite, right? Where we assume, like for a voltage source that's injecting energy into the system, the current flows in the other direction, right? It flows upward. So this active sign convention is what gives us the direction of EAT. It shows that the current, so we have EA of t plus minus, and then we have the current flowing like that. Yeah.
From the picture above, was EA from like the A axis to IA, or is it from where IA goes into the...
So the axis actually has no. I mean, this is a value that's related to the direction of the rotor. EA is an electrical value. They're not. They're not even in the same.
Yeah, but are we like saying EA is reference to the center of the rotor, or no?
No. That's you can always. This EA has nothing to do with the placement of the rotor itself. It's just trying to show that the voltage potential between the two ends of the wire is going to be EA.
Okay.
So we can almost like say like that.
Yeah.
That expands from there to there. Okay, so there are two forces that induce the EMF on the stator windings. One is going to be the rotation of the field winding, which we've been talking about predominantly so far. And two is going to be what we call the armature reaction. I don't know if I've made it clear, right? Armature, stator, same. They're synonyms for one another. Okay, so now getting more into that. Section 9.3.1 discusses the induced EMF from flux linkage with the field winding. All right, so we'll go through the first one, then we'll go back and talk about the armature reaction. And our goal is to so let's start by using Faraday's law to define the relationship between the rotor and the stator and how that gives us our EA. Okay, so equation 265 from the textbook. So we know that EA of t will be equal to the derivative in time of the flux linkage as it changes. Okay, that's also equal to, we have some substitutions because we can pull out the number of turns and say that this is equal to the change in flux with respect to time. Right, this comes from equation 262, which says that lambda is equal to n times phi, and we know that n is constant, and this is just our good old Faraday's law. Okay, so let's draw waveforms to illustrate how this derivative may work. Okay, so I'm going to start off by drawing the flux. So flux is going to be in green. And so 2, 4, 6. Okay. If that's our phi t, this is going to be the point that's the point at which our rate of change of phi with respect to time is going to be maximum, which means that our induced voltage, EA, which I'm going to show in gray, is going to be maximum at that point. But this also makes sense because one's a cosine, the other's a sine, vice versa, right? So when we take the derivative, there's going to automatically be that 90-degree phase shift. So what we're going to end up with, and here you can see the rate of change is 0, so we'll end up with a 0 value there, and then again the rate of change is minimum, so we'll end up with a waveform that looks like this. So that is going to be our EA of t waveform. Both are going to have the same phase. Not the same phase, sorry. Both are going to have the same period, and they don't necessarily have the same amplitude. I've tried to show that by making their heights a little bit different from one another. Okay, before we move on, let's talk about, well, does anyone have a textbook on them? I never read my textbook with me. For 1 second. There's a picture I wanted to add some detail to. Okay, so we can So what we're going to do now is try to include the rotation of the magnetic field. I know we've been talking about the flux linkages and the rate of change of flux, but all of that really has to do with the rotation of the magnetic field. Okay? The flux linkages are maximum when the magnetic field is lined up. The flux linkages are minimal when the magnetic field is perpendicular. So it makes sense to try to relate this back to the angle of the magnetic field. So what we have is if this horizontal axis is the A axis of the stator, and then what we have is a magnetic field, so this is BF, that is rotating this way, okay, at a speed of W synchronous, right? Now, the length of EAF right, that grows longer and shorter with the direction of BF. When the field winding lines up with the A axis, right, the length is going to be maximum, and when they're perpendicular, their length is going to be minimum. This shows sort of similar what we see on the previous, well, what we see right here in this graph. Okay, so how can we relate EAF to the magnetic field? And you'll see here all that EAF is the phasor representation of EA of t, right? EA of t is the instantaneous value. EAF is a phasor value. Same thing. The subscripts AF refers to it being a product of the mutual inductance between the phase A and the field winding. So A as in A phase, F as in field winding. Okay, so equation 9.1 from the textbook tells us that EAF is equal to, we'll explain this in 1 second, negative J KF BF of 0. Now BF of 0 is the vector at time equals 0. Okay, and so the vector at time equals 0 will be essentially, and I'll include it in here, that's the position. That's BF of 0. It'll be standing straight up. And a lot of these values are defined by the textbook for our purposes. So, I mean, again, there is no where we set time equals 0 is arbitrary for our, right, we can set it wherever we want, but we're going to do it in such a way that it makes our math work out. So for our purposes, that's the reference position of the magnetic field. BF0 is standing straight up. And it's perpendicular to the A-axis. Okay, so now usually I do a pretty good job in these notes of giving the steps in between, but here it's a little bit, it must have been close to the end of one of the lectures. Okay, so what I did in the notes here, which I don't see anywhere in the book. Let's take the magnitude of EAF. And if we take the magnitude of EAF, that'll propagate through the rest of the equation. Negative J will stay the same, KF will stay the same. Now we're going to take the magnitude of BF of 0, but in there we have to multiply by J because these two together give us BF of 0. The reason being because BF has a 90-degree rotation with respect to EAF. And so what we end up with is these two J's will cancel out. So it'll be J times J is -1 times -1, which gives us +1. So we see the magnitude of EAF is dependent on a constant times the strength of the magnetic field at time 0. So that makes sense. Right, the stronger the magnetic field is, the greater the induced voltage magnitude will be. And then, like most things in engineering, there's a constant involved, which is going to represent the air gap with the permeability of the ferromagnetic materials and all kinds of different stuff that's boiled into the design of the generator. Okay, so this is one piece of the puzzle. If you remember, going all the way back up here, we said there are two forces that induce an EMF on the stator winding. One is the rotation of the field winding, the other one's the armature reaction. So we have the expression now that defines the first one, which is the induced EMF due to the rotation of the field winding. We've got an expression which relates to BF, the magnetic field generated by the field winding, so that checks that box. So now let's move on to the second piece, which is the armature reaction, and we'll talk about exactly what that is. So section 9.3.2 is induced EMF due to armature reaction. Okay. So what we'll see is that the armature EMF is going to be dependent on all the different currents. IA, IB, IC. Not just IA. And that's because these coils are magnetically coupled. If you remember our discussion of self-mutual inductances, there'll be a mutual inductance not only between the A phase coil and the field winding, but also A phase, B phase, C phase. And so in order to analyze the effect of this coupling, we are going to define individual magnetic fields for each phase. Okay, so this is equation 9.2 from the text. So we have B, IA, we have BIB, and we have BIC. So BF was a magnetic field that was induced by the field winding. These are the magnetic fields that are associated with the armature windings. So the armature reaction, what that describes is how phase A reacts to the currents flowing on phase B and phase C. So each armature winding, stator winding reacts not only to the field winding, but also to the magnetic fields generated by the other windings. Okay, so BIA equals K1IA, and we'll explain this in a second where this is coming from, times e to the j 0 degrees, K1IB times e to the j 2 pi divided by 3. Okay, so let's explain all the different pieces here. So the first thing is that these represent the spatial differences in the phase windings. Specifically, right, if we're analyzing the armature reaction with respect to phase A, then obviously the phase A coil lines up with 0, so there's a 0 degrees differential. The phase B coil lines up with a 2 pi over 3 radian differential, and the phase C lines up with a 4 pi over 3 differential. The machine constant is constant. Okay, our machine coefficient is constant. That doesn't change. So this K1 is the machine coefficient. And it's the same for all phases. Right, that's because the air gap width is not changing, and the ferromagnetic material, and essentially all the different pieces that make up the generator right there, changing from phase to phase. And then in here, in IA, IB, and IC, although we haven't included that mathematically yet, that's where we'll have the temporal difference in the magnetic field strength, right? Because IA, IB, and IC will all be separated by a certain distance temporally. And what we can do is later on, which will be the next step, is include that temporal difference and put everything in terms of IA with a rotation associated with it. All right. So now what we can do is we can calculate what we'll call the resultant or the equivalent flux density distribution by summing these together. So we know that the armature reaction will be dependent on all three of these components summed together, including, if we're talking about phase A, including BIA, right? There's a self-inductance value. The magnetic field induced by phase A will have an effect on itself, on the way that it operates. Okay, so equation 9.3 says that our BAR, which is the total armature reaction, remember that's what we're dealing with right now. We talked about the effect of the field winding on the stator winding, and now we're doing the armature reaction. That's going to be equal to K1 times IA e to the J0 plus IB e to the J 2 pi over 3 plus IC e to the J 4 pi over 3. And like I said a second ago, right, we can write these in terms of IA if we want to, which we do, and that's what we're going to do now. So let's redefine those currents. So equation 9.4 from the book. Right, we know that IA is equal to its own magnitude, which we'll call IA magnitude, right? Actually, let me make a quick correction here. It's equal to square root of 2 times IA magnitude, and we're going to call that value IA peak with that little hat on top. and times cosine of omega t minus whatever the theta, the reference theta is. We know that IB will be right? That's just, we're assuming balanced operation right now, so the amplitude of IB will be the same as the amplitude of IA. And IC, same thing. Same amplitude, cosine, omega t minus theta, minus, or we could do plus 2 pi over 3. So we can sum these three together. Like what's shown above. This right here is going to be our omega sync, the synchronous value. And so if we combine these three equations together, we get equation 9.6, which says that the total armature reaction, which is represented as a magnetic field strength intensity, is equal to a new machine constant, we'll talk about where that comes from in a second, times the amplitude of IA, e to the j So, we're not going to go through and derive each part of this, but we know from previous or prior parts of this course that summing the three of these together, there's an identity that allows us to combine the three together into one. So the resultant of summing these three together is that we take equation 9.3 based on three different currents with the assumption that they're balanced, and we end up with one where it's only dependent on the amplitude of what we call the phase A, which is the armature current for all three, and the synchronous rotational speed. All right. And so using these equations, we see we can represent all of the mutual inductances between phase A and the other phases in a decoupled manner as this single self-inductance. So what we're doing is we're aggregating it all together into one piece and representing it mathematically, taking 9.3 and representing it as 9.6. Yeah.
Is there a reason you just switch
Yes, they're different. They're different constants because. And do they give the value in here? Hold on. So in order to, I don't think they go through and define the difference between K1 and K2, but when you do that sum, there's some additional coefficients that get pushed in there. A factor of 3 in addition to some other stuff. So K1 and K2 are both machine constants. They're different machine constants. And when you do a problem, if you do have a problem that goes into